Okay, good morning everybody. It's a really great pleasure to be in Wistig again. It's the third time that I come here, and every time, as Claire was mentioning a little bit this morning, for me it's a little bit difficult to go back to France because it's a fantastic environment. So we are going to stay with enzymes this morning, but I will talk a little bit about something a little bit more physical or physico-chemical. And I will try to show you in the next 10-15 minutes how we can use enzymes to do something which in principle should not be possible. Okay? So this is why I'm saying we are trying to fight against thermodynamics, and I will start with a very simple comparison. So imagine you're sitting on your bicycle and you don't do anything, but you just drive downhill, and then at some point you stop paddling, and you hope that on the other side you will be able to get up to a summit which is higher than the summit where you started from. And then everybody will agree with me that this is not possible. Okay? Even if there is some very nice incentive on top of the mountain, you will not get there. Okay? This is just normal thermodynamics which tells you it's not possible. And this is also applying for not only people who are biking, but it's also applying for chemical reactions, and this is the topic of this morning. So when you replace the beer and the guy on the bicycle by an electron, so you start at a certain level, and actually you would like to bring the electron which is falling down the hill, you would like to bring it up the hill which is bigger or higher than the first hill, then this is not possible, and we are going to have something that thermodynamically is forbidden. In the case that I'm going to explain you this morning, we are trying to use glucose reacting together with oxygen, and that's where the enzyme will come in. And we would like to use this reaction to produce hydrogen. And if you look at the thermodynamics, and I will go into the thermodynamics a little bit more in detail later, it's not possible. Okay? If you just look at the numbers, this is a reaction that you cannot achieve. However, there is a way to get around this thermodynamic or apparently forbidden thermodynamic situation, and this is illustrated by the following. Now let's imagine you are not having just one electron sitting on your bicycle, but you have two electrons sitting on your bicycle. You run down the hill, and then when you are at the bottom of the hill in the valley, you get rid of one of these electrons, so you throw out one electron, you sacrifice one electron, and you use the energy of this sacrificed electron to push up the energy of the remaining electron. So this is more or less the philosophy that we are going to try to apply to our electrochemical reaction. And in this case, you can eventually, if you use some tricks, and I will show you these tricks, you can reach the hill of the hydrogen despite the fact that you started at an energy level which in principle should not allow you to do this. Okay? So this is working, and I will try to show in the next few minutes how we can make this. So we have to solve two challenges. The first challenge is that somehow, because we are doing electrochemistry, somehow we have to play with voltages. So we get from the first reaction, we get a certain voltage which is not good enough in order to drive the second voltage, the second reaction, because it needs a voltage which is higher. And so we need to boost the voltage. This can be done electronically. And we have a second problem, because if you try to drive two electrochemical reactions in the same reactor with two independent electrochemical systems, but they are sharing the same solution, normally this is also not possible, because you cannot have in the same solution two different potentials, two different electrochemical potentials, because you have a short circuit by the electrolyte. Okay? So somehow we have to find a way to uncouple the electrochemical system which is providing the energy and the electrochemical system which is using the energy. Normally you do this by introducing a wall, okay? Then you have a normal battery system, but we would like to do everything in one single solution, and then we need to use another trick. So we are going to solve these two challenges, And so I'm coming back a little bit to the thermodynamics, so the details of the thermodynamics. So normally when a reaction occurs spontaneously, all of you know, it's what you learned in high school, that delta G has to be negative. Okay? So let's look at this reaction that I was mentioning already. So we would like to transform glucose, so we are oxidizing glucose. It should give us gluconolactone, and because this is the oxidation product, we would like to use the electrons that we recover from this oxidation, we would like to use it to transform protons into hydrogen. If I make the energy balance, as you will see in a second, the energy balance of this reaction is plus 16 kilojoule per mole. So everybody will say it's not possible, it's not a spontaneous reaction. And indeed, if you look in detail, the two reactions that I'm going to use intrinsically, there's the first one where you burn the glucose together with oxygen. This gives you the gluconolactone and water. This is the energy delivering reaction, so minus 223 kilojoule per mole. This is possible. But on the other side, the reaction that you need to carry out is the electrolysis or the splitting, the electrochemical splitting of water into oxygen and hydrogen. And this, if you look at the thermodynamics, it needs 239 kilojoule per mole. So now you make just the difference, 239 minus 223, it gives a positive value. So the conclusion is, it's not possible, okay? But as I said, we can do it by using two tricks. So the first part, the left part, will be our energy delivering reaction. We are going to carry out this reaction of glucose oxidation and oxygen reduction in a so-called biofuel cell. That means it's an electrochemical cell where you place enzymes on the electrodes. One enzyme is oxidizing something, the other enzyme is reducing something, and you get electricity out of it. And then this electricity, we are going to use it to electrolyze water in an electrolytic cell, which is the second electrochemical cell. So these two have to communicate, and it means they have to have the right potentials to do the job. A little bit more detail in terms of potential. So again, we are having here the characteristic thermodynamic values. If you look, what can typically produce a glucose-oxygen biofuel cell, just theoretically, you can get at the maximum, you can get 1.16 volt from such a device where you have one electrode which is functionalized with glucose oxidase to oxidize glucose. The other electrode is functionalized with bilirubin oxidase where you transform oxygen into water. The final voltage is 1.16 volt. On the other hand, if you look at the decomposition of water, you have to have at least thermodynamically plus 1.23 volt between the two electrodes, one which is oxidizing water and the other one is reducing the protons. So we have the same dilemma. We have one electrode or one electrochemical cell which delivers 1.16 volt and the other one which needs 1.23. It's not going to work, at least not like this, okay? So we have not enough potential to drive the water splitting, and also for the moment we don't know how to combine these two systems in a single cell. That means sharing the same electrolyte. This is schematically again the same problem, but just even more dramatic, because the values of potential that I just showed you, these are the theoretical thermodynamic potentials. In reality, the situation is a much bigger disaster, because if you look in reality into the kinetics or energetics of a biofuel cell, instead of the theoretically possible 1.16 volt, typically you get even less. That means around 0.6 volt, 0.7 volt. And on the other side, you replace in reality the theoretical value of 1.23 volt, you need at least 2 volt to drive the water splitting. So now you have a bigger difference that is even more forbidding the reaction to go. We have something less than 0.8 volt on one side and we need more than 2 volt on the other side. So we have to boost the voltage from 0.8 volt to 2 volt. and this is something that we have to combine with a decoupling of two electrochemical cells. Because, and the first line is only a normal battery, if you put two electrochemical cells, as I said before, into the same solution, you will have a kind of an electrochemical short circuit. So we are solving this problem. The first problem of the potential we are solving by an electronic device which is called a boost converter. So we have still two separated electrochemical devices, one which is delivering the energy thanks to the biofuel cell, the other one which is using the energy, so we are electrolyzing water, and this is the first way how we can do this reaction. But finally we would like to have these two cells combined into one, but if you combine them like this in one single cell, there will be no production of hydrogen, because there's an electrochemical short circuit, just like in a battery. When you remove, in a battery you remove the wall separating two batteries, you will have no driving force, okay? You make a short circuit. So in order to solve this second problem of electrochemical short circuit, we have to use another electrochemical trick, or an electronic trick. It's called a flyback, which is decoupling in time the energy production and the energy delivery. So this looks like this. The two electronic tricks, actually the boost converter uses the voltage that comes from the biofuel cell and the current that is delivered by the biofuel cell, and it's converting this voltage in a higher voltage, but this has a price, and the price is that you will have, instead of the initial current that you had here, you will get a current that is smaller. You can calculate all this, so you can more or less fine-tune at will the potential which comes out from your biofuel cell, but the price to pay is that you get less current. The second electronic trick is this flyback. I don't have the time to go into the details, but essentially what you do, you come in here with your energy from the biofuel cell and you store it temporarily in this part of the electronic circuit, and then only from time to time you open the electronic circuit to couple this energy into another circuit, and then you deliver it to the other device, which is the electrolysis device, but they are not connected simultaneously, so there is no more this problem of electronic short circuit. So globally what we set up in our experiment is here the combination of these two devices. So we have here the input, this is our biofuel cell, oxygen reduction, glucose oxidation, it gives us some voltage. This voltage is boosted up by the boost converter, and then we are decoupling this voltage with the flyback, and we get finally a voltage and a current which allows us to electrolyze water. So we are going to produce oxygen here and hydrogen here. And this is how it looks like. Can you start this video, please? So this is the first setup where we still have two compartments. So we have one compartment which is delivering the energy thanks to the enzymes which are working on the anode and the cathode, so the biofuel cell. We push up the voltage, so we are starting to overcome this limit of thermodynamics in order to get hydrogen evolution, and you can see here the microelectrode which is delivering a nice stream of hydrogen bubbles when the biofuel cell is connected. When the biofuel cell is disconnected, there's no more hydrogen evolution. But we still have two separate compartments. Now the challenge is to combine them in one single compartment, and that's what you will see in the next slide. So we are going to put everything now together. We have the boost converter and this famous flyback where we are decoupling electronically the two electrochemical systems. Everything can be miniaturized. Here you have the two electrodes of the biofuel cell. In the middle you have your microelectrode. We start this video. And it's producing again hydrogen. As you can see, there's a nice stream of hydrogen. So we have managed to transform directly glucose into hydrogen. The Faraday efficiency is 100%, close to 100%. For sure we have to pay a price because the electronics is eating up some of our energy. So we lose more or less 50% of our power by driving the two electronic circuits, but we still get an overall efficiency of glucose into hydrogen conversion, which is 5%, which is quite reasonable if you look at other electrochemical or photochemical or photoelectrochemical systems. So we were able to overcome this challenge of producing directly hydrogen with a glucose oxidase, which is not supposed to produce hydrogen. Glucose oxidase is only digesting glucose. So if you have a lot of glucose as a feed, you could produce some high added value material like hydrogen. And we need no external power input. We can do everything in the single medium. We overcome the apparent contradiction of thermodynamics, and we can apply this very general concept actually to many other chemical and electrochemical reactions. This is just one proof of principle experiment. So all this has been published quite recently, and the conclusion is that we are able now to go up the mountain, starting from the valley, and apparently against thermodynamics, but for sure we cannot break the rules of thermodynamics. It's just because we have used these electronic tricks to solve these different problems. So this is the end of my story. Use of enzyme in a completely different context, but I think there's quite some important future of applications behind this concept. Thank you very much for your attention.